Hello, in this video we'll solve an exercise from the Hartshorne book about algebraic geometry. It's exercise, so it's from chapter 2, exercise 3.6. And we'll not solve the complete exercise, but just the part we're interested in. So let's say X is an integral scheme. And what we want to show is, well, maybe as I stated as lemma, I don't write it as show, but so the local ring O xi of the generic point xi of the scheme X is a field, so which will be called the function field of the scheme. And so that's what we want to show. And so let me first recall a few things. So a scheme is integral if and only if it's irreducible and reduced. So that's the first thing. And a closed subset of an irreducible scheme has a generic point. So that's important because we need a generic point here already in the statement. Okay, so these are some facts you might know from an algebraic geometry course, or if not, you can look them up. But now let's see the proof. So let's take a point in this local ring, so in this O of xi, and then let's take a representative of this point. So let's take S in O of V, where I mean with O, I mean OX, so that's the structure sheaf. So that should be a representative of Y. So what I mean is that S xi is equal to Y, and for some open subset of X where xi is in the subset. Okay, so we take this representative, and without loss of generality, we assume that V is a subset of some affine scheme, and then we can restrict even further, so we make V even smaller. So at first we say it's a subset of some spec A, for where A is just some ring, and furthermore then we assume that V is one of these basic open sets, so of the form D of F for some F in the ring. Okay, and now we are already in a good situation because we know what the structure sheaf of so what this O of V is, namely it's the localization of this ring A at F, and we also know this is an integral domain because our scheme is integral, so that's good. And now let's see. So now we take we have this representative S in OV in this integral domain, and which is again a localized at f, and then we can write s as sum a divided by f to the n for a in a, so for some a in a, and n a non-negative integer. Okay, and now we want to take inverses. And well, let's at first consider just in the field of fraction this element t, which would be the formal inverse, but so this would be in the field of fractions, and here it's important that we have an integral domain, so we have the field of fractions. And we don't have to consider it as an element in the field of fractions, we consider it as an element in the dislocalization of the ring A. And now let's see further. So at first note that df intersection dA is equal to dA times f. And what's important now is that dAf is an open neighborhood of our generic point. So we have this generic point psi, so which is the generic point, and as it's the generic point, it's in all these open sets. So let me again remind you, so the closure of this one point set is the whole space, which means that for all x and x and neighborhoods ux of x, so this means that it stands, and then we have the psi is in ux, so it's especially in this open set. So well, it's in every open set, so it's in this open set, and so we are basically done. So what we do now is we restrict the section S to dAf, then we multiply it with this element here, so that's well, so that's O of d of A, and okay, so we restrict this to also to the same set, and then we get this is 1, so that's just by the definition of t, so t is the inverse of S, and now we are done, because now we just take equivalence classes. So if we write the equivalence class, so this is in this ring here, and this is also in this ring here, then we get that this is also 1, and we get that this ring, this local ring, is a field, which we wanted from the beginning. Okay, so that's it, and that's quite important, because now we have this function field here of the generic point, and that also plays a role, for instance, for divisors. So if you care about divisors or the Picard group or stuff like that, then you need this statement. But well, for divisors, often you need more than just an integral scheme, but you want some further conditions on the scheme. Yeah, but that's it for that video. Probably, so there will be more videos like this, which will be exercise-like, and also some more videos building upon another, probably a little bit about definition of schemes and stuff like that, but it will be mixed in the level. So this video presupposed quite a lot, but there will be other ones which are more accessible. So thanks for watching and have a good time. Bye.